Do not disturb. Yeah. What's up?
Oh, so earlier this week I filled in like next week's for the check-ins, like the
The Project 3
yeah
check-ins?
in person project two check-ins. So we get when I know they're like you're supposed to fill them out by today, right? We get like an email and then that tells us like when like if we actually get like got assigned like the one we signed up for.
I think you just show up to the one you sign up for.
Oh,
Yeah.
I thought it was like a waiting list system.
I'm not sure, sorry.
Huh. Hey, yeah,
Yeah. No worries.
I have a question.
Yeah.
Let me get it. Okay. What's up? For the project,
Mhm.
how will they know that we use AI to like double the requirements of the points?
We won't. It is an honor system.
Oh, wait, do we like actively like have to tell you?
If you use AI, then we trust that you will tell us and that you'll,
How do we tell you?
there should be a pilot program like request.
Oh, okay.
Yeah.
Okay.
Uh, yeah. It is an honor system. We will trust what you are doing. We will still verify. And if we see AI generated code or code that looks AI generated and you are in a pilot program, then we might give you a nasty email. But
Okay.
please don't make us make nasty emails. We do not like making nasty emails. Besides, you're paying good money to take this course.
No, I'm not saying that. I'm just saying theoretically.
Hypothetically, sure. Can people on Zoom hear me? Great. Hello.
I got a hello to the for everyone else.
Yes. Okay, good. This thing's set up right. To double check something. What do you mean tri-weekly torture session?
What's that? Huh. I think someone doesn't like our class.
Hmm.
I don't know. I don't know. Is that late drop? Okay.
Oh, no.
Harsh.
That's harsh, yeah.
I don't know if I've gotten out. Hmm.
Why is this mic stuck on? Can people hear me right now? The mic audio thingy is looking like it's just stuck right now. Okay. I don't know why that's that way then. Yeah.
Have you played SU?
Yes.
It's so good.
It's a good
I
game.
started playing it again this week. I played through a lot of it a few years ago. It's like it's just long enough ago that I don't remember the puzzles.
Yeah.
I sent it to Call Hilfiger actually 5 years ago. I was like, you need to play this game at home.
Baba is fun. Yeah. I don't think I finished.
I never felt it.
Yeah. The meta area is
Which meta, I get to the meta level. Yeah. I got I was stuck on a puzzle the other night or the other day, and then I like when I was going to sleep figured it out. And then
yeah.
I did it yesterday, which is nice.
That's good. Baba's very good with that.
It's really nice.
Have you done like Steven sausage roll? Which one? Steven sausage roll? No. There's a few ones. Tacoret down the bun burrows is also a good one that I've heard about.
Huh. Yeah.
Definitely look those up. All right. Good afternoon. How's everyone doing? 2 more days. Or 3 more days, depending on how you count them. How's Project 3B going? How many people are done with 3B? Nice. How many people still have a bit more work to do? Getting it done over the weekend? Yeah. How many people are satisfied with their project right now?
Oh, nice.
Feel good about how the project went? Huh? Yeah. You're going to be working on this after the project? Yes. That is exactly what we want you all to do. If you have a good project so far, it is always possible to keep working on it. In fact, we're actually going to have a showcase day. So we've booked the WAS May 11th. That's the Sunday after our week, so right before finals. And we're just going to have people showcase their projects. We want to see what you've done. We want to let you show off your cool projects to other students. It's just kind of a new idea we're having this semester. We'll see how it goes. Just out of curiosity, how many people would be interested in showcasing their projects at this showcase? Few people. How many people would be interested in showing up to like see these projects? Few more people. All right. So we have a registration link here. I think right now the form is currently set only for people who are registering to present their projects. We'll see if we can add also attendees sign in just to see how many people are interested. But yeah, I'm excited to see all the cool projects y'all have made. It'll be fun. Also, the TAs were asking me if it's fun.
Oh, let's do it. Yeah. Throw some money in some pizza. I'll buy a pizza.
All right, we're getting pizza for this too.
I'm getting pizza. You get the RSVP somehow, right? We should get some kind of RSVP.
Yeah, we have it.
Okay.
Yeah. Although it's currently only for presenters, not attendees, so it will make sense. Anyway. So let's get started with today's lecture, shall we? All right, so today we're going to split the lecture roughly in half. The first half of the class is going to be just finishing up our sorting algorithm discussions. Just getting through the last few pieces of radix sort. The second half, we're actually going to go into just some algorithm design practice, kind of a brief overview of the rest of the class. This is our last mandatory lecture. Next week is going to be 3 optional lectures, all just like interesting side topics of material we've covered so far. Uh, so we're kind of nearing the end of our material. So let's get started with just a quick question. So merge sort, we said, required theta and log n comparisons. And if the comparisons are all constant time, then it is going to take n log n time to run merge sort. We saw that that's going to be kind of the most efficient algorithm possible. Now, what if we worked on strings of arbitrary length? So if we had merge sort done on a list of strings that were length w each, what would be the actual runtime of this merge sort? Is it necessarily going to be the same n log n, or do we have to take the w into effect? Let's take a minute or so to discuss with your neighbors.
Still been here now. It's still been more number of people. This is simple. 5 minutes ago.
All right, let's bring everyone back. All right, what do people say? How long does merge sort take if we're running it on strings of length w? Yeah. Yeah. O of w and log n. Can you explain why?
For example, you also have to compare the object. So, a string is an object, you have to form some header, and that would take the length of the string times.
Yeah. If we're dealing with a string comparator, that's going to take w time in the worst case. And if we have n log n comparisons, that's w times n log n total time. Is that always going to happen? Is it always w n log n? No.
It can be n log n as well if all the strings are distinct first letter.
Yeah, okay. If all the strings are distinct on the first letter, though, then the comparisons still take a constant amount of time, and we end up with an n log n again. Yeah, that's a good point. Depending on how the strings behave, you might get somewhere between n log n and w n log n. So let me ask another question. LSD sort, it had a runtime of wn, and merge sort had a runtime between n log n and w n log n for these strings. So which one's going to be better is dependent on what specific data set you have. So can anyone come up with the data set that will make LSD sort faster? And can anyone come up with an input set that will make merge sort faster? Let's talk with your neighbors for another minute on this.
Yeah,
All right, let's bring everyone back together. All right, what did people say? When is LSD sort faster? Yeah. Larger data sets, can you explain why? Mhm. Yeah, when n is really large relative to w, uh, then LSD sort is going to be faster, especially when w is less than log n, then that's just strictly better. Any other cases? When might LSD sort be better? How about merge sort? When might merge sort be better? Yeah.
You have long strings, the W is bigger, like large compared to
Mhm. Yeah, when W is really, really large, like the strings are all really long, and if the strings are very distinct at the start. So that way the merge sort runtime doesn't have to go through as many letters before you find a comparison. Then merge sort is going to be faster. It's a good point. Another case when LSD sort will be faster is if the strings are like really, really similar to each other. If all the merge sort comparisons cost theta W time, uh, then LSD sort is better because it's Wn compared to Wn log n. So you are going to get better runtime with merge sort or with LSD sort if you have very similar strings as well. So depending on the specific data set you're working with, you might find that radix sort is better than merge sort. Of course, if you're not working with strings or anything that is stringy and you only have comparisons, then generally speaking, your merge sort is going to be better because you can't really do an LSD sort. All right, let's quickly pivot to another topic. Imagine that we're trying to radix sort integers. So one of the concerns that we have with radix sorting integers is that we don't really have a char at method. So how do you actually LSD radix sort an array of integers? Uh, Anyone have any ideas how this would work? Yeah.
It's like odd.
Yeah, use mod 10 somehow, divide by enough of power of 10, then take the mod. That's effectively taking like each individual digit one at a time. Uh, that's a good approach. Any other approaches anyone might have? Yeah.
Um, maybe look at the like the binary representation compared to rows and months and do analysis on
Look at the binary representation. Yeah, it's very similar to the decimal thing. The main difference is that we're using binary because our computers think in binary, so it's going to be probably more efficient to look at the binary representation of the number instead. That does mean that we have a lot more digits. General rule of thumb is 3 digits of decimal correspond to 10 digits of binary. So we've approximately tripled the size of our W value. It's going to be less efficient, but it does seem like it might work better because you're dealing with actual binary instead of decimal. Yeah. Here's kind of my answer here. So we could just convert it into a string. That works, technically. Uh, since the maximum Java integer is just about 2 billion, the longest possible string we could ever have is 10 or 11 characters long, depending on if you count the negative sign at the start. You could modify LSD sort to work natively on integers, like using this idea of you taking the digit. There's probably some function that does this. The easiest way to do that would probably be to take the number divided by a certain power of 10 and then mod it by a certain power of 10 as well. Yeah. But there isn't really any reason to stick with base 10. We could just use a base 16 integer, or base 256 integer, 65,536. All of these are powers of 2. And if you use the power of 2, then it works really nicely uh, with the underlying binary system that the computer thinks in. So if we interpret 512,312 in base 16, then you get the sequence of digits 7, 13, 1, 3, 8. Now the 13 is a number bigger than 10, but it's treated as a single digit. We use normally a letter to represent the 13 digit in base 16. 13 is what, D? Sounds D-ish.
Yeah.
Yeah, it's D.
Yeah. Right.
Yeah. We could also do base 256 if we really want to. 209 is a single digit character, if you can imagine that. But a computer can think in terms of that. It's perfectly fine with thinking of 256 distinct symbols to represent 256 distinct digits. So depending on the size of R, you're going to get different values of W. If you have R equals 10, the maximum Java integer is going to be 10 digits long at max. If you treat R as 16, you're going to have only up to 8 digits. That's just how the math ends up working. R equals 256, you have up to 4 digits. If you go all the way down to R equals 2,147,483,647, which is the maximum possible integer value of an int, uh, then you have exactly 1 digit for every single possible number. That basically is the same thing as counting sort, because you're basically just creating an array containing every single number. So generally speaking, the larger the value of R you make, the fewer digits you're going to have. At the same time, the fewer digits you have, the larger R needs to be to fit everything within those number of digits. Now, our runtime we said was WN, right? So what's the problem with just setting R equal to 2 billion? Anyone? Is there a problem with just setting R to 2 billion, get W equal to 1? Yeah. Yeah. If you remember, it wasn't just WN, it was WN plus R. And we said R was small enough that it didn't matter. But if R is really big, then now all of a sudden you have a big R to deal with. And the larger R gets, the slower radix sort becomes. You have an R times W component associated. Sorry. Now, if you just use a computational experiment, just look at how it works, then you actually see that if you go better and better, if you use more and more digits, it does peak somewhere around base 256. Effectively, what's going on is that if you about half the value of W, then you approximately square the value of R. So this means that at some point, you get really bad diminishing returns when you increase the base. So we did these computational experiments. Quicksort actually took like 11 seconds to sort a million integers. If you switch to radix sort, then just radix sort at base 16 ends up causing a runtime of 3.6 seconds. The sweet spot turned out to be around 2 to the 8, base 256, which got us 2.28 seconds. If you went all the way up to base 2 to the 30, base 1 billion, then you ended up with a runtime of 20 seconds, which is just significantly worse than anything else. So you will need to do this separately in every single computer you try to run this on. You might have different experimental results than I would. It isn't really easy to generalize this because it does depend on exactly what types of operations get done. But overall, it does seem like certain types of radix sort do tend to work better on integers than your standard quicksort. Any questions up to here? Okay. So we've kind of covered a lot of different sorting algorithms, and this is kind of where we'll finish off our sorting stuff. We've seen a lot of these different flavors of this: comparison sorts, radix sorts, alphabet type sorts. Each one can be useful in different circumstances. But the big thing is that we want you to think carefully about which ones you want to use. A general rule of thumb is that there's going to be a lot of different ways to solve a problem now, and it's up to you to decide which one is the best approach. It's not sufficient to say, I found a solution to a problem. You now need to think, I want to find the best solution. And what you define as best is going to depend on what systems you're working on. You might have a system that has really fast memory accesses. You might have a system that has really small memory components entirely, and you need to increase your runtime to compensate. So here's just a quick overview of all of the sorting algorithms we discussed. We had selection sort as kind of our first initial idea. It's not really used too often, but if we heapify it, then we get heap sort. That's still not used a lot because merge sort ends up being faster in general. Insertion sort works really quickly in the best cases. It's really quick for small lists, but if you have longer lists, then you might want to do quicksort instead. For small alphabet sizes, if you only have like 5 distinct values, then counting sort is really effective. If you have larger ones, then you want to use LSD or MSD sorting, which kind of relies on counting sort as a subroutine. Uh, and you can kind of use this in a lot of different cases. Depending on the data set you're working with, you might prefer different sorting algorithms. Quicksort, we said, was really useful when you have uh, primitives types because you don't have a need for a stable sort. Merge sort is more useful for stable sorting. That kind of concludes our discussion on sorting in general. During the data structures part of the class, we actually discussed more of what we would call the search problem, which, given a list of data, gives you data that you really want to look at. So lists, for example, were a search problem where you have the data ordered and you want to find a particular item in the data. Maps and sets, they're variants where we don't have an order. Maps, you have a key, you look up its corresponding value. Priority queues, we only look at the items that are smallest. Disjoint sets, we're just checking to see if you can connect or if two things are connected together. Here's just the ones that we covered. As it turns out, these do have interesting connections to the sorting algorithms that we came up with. So sets and maps, you could create them using 2-3 trees, red-black trees, hash tables, tries. Uh, but if you look at how these comparison algorithms work, we saw that we could also similarly use these data structures to solve them themselves, right? We could use a heap to do sorting algorithms in the same way that you can use a heap to solve the priority queue search algorithm. You could use a binary search tree for quicksort, and there's probably some variant of quicksort that uses an equivalent 2-3 tree something. Maybe? I have no idea. It could exist. It sounds like it'll probably be slow anyway, but you can imagine just trying to build these kinds of interesting sorting algorithms just by using the existing data structures that we've talked about. So, and similarly to how we used some data structures to build others, we mentioned that, for example, Java's set class is just the same thing as Java's map class, but ignoring the value. Similar to that, you can use sorting algorithms to solve other sorting algorithms. We use LSD sort to solve, or we use LSD sort because we had a counting sort that could work as a subroutine there. So these searches using compare to, they're analogous to these comparison-based approaches. The hash coding equals is roughly analogous to the integer sorting one. The tries, they're similar to radix sorting in behavior. So if you really wanted to, you could call the first two like comparison sorts, like tree sorts. You could say that the partition sort is more like hash sorting-ish. Not really. And you can call the LSD sort, MSD sort more like try sort because they do kind of use similar concepts. Now, there's plenty more to look into. A lot of these ideas can be mixed and matched, and they're a great source for exam questions that we write. We like being creative in these kinds of things. But you can kind of think about these types of questions. You might ask yourself, what could you do? And these are fun experiments to try work around. What if you use quicksort for MSD radix sort instead? Could we use an LLRB to improve radix sort somehow? There's all sorts of questions you can ask, and this is kind of the reason why this is such a rich field. Why it's so easy to just come up with your own data structure, own type of tree, or own type of sorting algorithm. It's why there's so many of these types of sorting algorithms in existence. Because if you just ask the right questions, then you come across an entirely new way to solve the same problem. So we saw this sorting algorithms video already. Now that we have a bit more information, you can go back over and see a few more of these sorting algorithms. But you can ask yourself how each of these algorithms work. And we only covered like what, 5, 6 algorithms total, maybe 10 at most if you count BOGO sort and bubble sort. But like, there's quite literally hundreds of these sorting algorithms. And if you're curious, you can definitely look into these and see more about how these were built. All right. That concludes our sorting section. Before we continue on, does anyone have any questions? Okay. So I want to just finish off this class by discussing how you can design algorithms. Algorithm design tends to be a part that students have the most difficulty on because it is kind of this, it's not easy to say what a right answer is here. Often it's you're creating a new algorithm using kind of these tools. So we've given you a list of data structures that we've worked with. Lists, decks, disjoint sets, sets, maps, heaps, graphs. All of these things were things that we've covered. But when you're working on actually solving an algorithm, trying to create a new algorithm, it's not useful to think in terms of, oh, I need to use a list because it stores a collection of items in order. I like to think about these data structures in terms of what problems they're able to solve, kind of as tools, right? So the way I like to imagine these are like hammers or screwdrivers, right? When you're dealing with a hammer, you're not thinking, oh, a hammer is a tool that is composed of a block of metal attached to a piece of wood, with the metal composed of 99% iron in this case, but sometimes you use a nickel iron hammer. You're not thinking in terms of that. You're thinking a hammer as something that if I had a nail and I wanted to hammer it in, then I have a tool to do that. And now you're thinking, no, you're not thinking I have a block of metal that I can whack stuff with. You're thinking I have the ability to hammer in a nail if I wanted to. So here's what I would say we've solved effectively. Given a collection of n items, if you have an order to them, you can sort them in n log n time. That's our sorting problems. You can add to the collection in constant time using a set. You can iterate over the items using constant overhead. So if you look over a set of n items, that takes n total time. You can repeatedly find the smallest item in log n time if you allow your adds to be log n as well. So these are problems that you can solve. If you're given a set of n distinct items with no order, you can add to or remove from the collection in constant time. You can iterate over the items. You can associate values with items. So you can do like a dictionary or a map without any additional overhead. You can check if a particular item is in the set in a constant time. So if I had a list of, let's say, a dozen different things, I can see if any one thing that I'm thinking of is in there easily. And given a graph, you can find the shortest path between two vertices in fast time. You can find the minimum spanning tree in fast time. You can figure out whether two nodes are connected in a really fast time. So these are all just kind of how I would think about our data structures. I'm not thinking about them in terms of what data structures I'm using. I'm thinking about them in terms of what problems I can immediately say, oh, I've already solved this. I don't need to worry about them. So any questions here? It's kind of a different way to think about data structures. You're not thinking about the structures themselves, more the problems. Yeah. So it's always useful to go over some practice. So let's try these out. Now, algorithm design is kind of the most creative part of 61B. It makes up a big portion of CS theory, and it's often the first step you have to do when you're creating a new algorithm, right? You have to first ideate over it. I always say that when I'm writing a new piece of code, I spend at least half the time on a whiteboard trying to figure out what I want to do instead of actually typing on a computer. And that becomes more and more common as you get higher up, as the problems get harder and more complex. These problems also end up getting tested in interviews for the similar reason. They kind of test your like ability to build something new given a set of tools. There's unfortunately no easy trick to solve these. The easiest way to get better at these is through practice. Fortunately, there are a lot of good practice websites you can use. As it turns out, the people who do computer science and come up with these problems are also really good at making websites. Who would have guessed? So we have LeetCode and Codeforces, which are similar to interview questions, although the harder ones veer more into like competitive programming territory. Shout out to ICPC, by the way. They're a very great group. I had a lot of fun with them. Advent of Code is actually a really nice one It does yearly code challenges that release a problem a day in December. Every time I run this lecture in the fall semester, I shout them out because they're kind of fun to play around with. Uh, I've heard that it's useful both to like practice your algorithm design skills and to practice a new programming language. Project Euler is more mathy than the others. It's focused more on coming up with these new um, programmatic solutions or new algorithms. So that's going to be very useful if you want to like go into like really hard 170 cell algorithm design. So for the rest of today, I'm just going to give you some like practice problems. We'll just be practicing things. I'll give you a few minutes to try out the problem, and I'll give you an approximate difficulty of each question just based on my subjective belief. Now, different people are going to have different subjective ideas on what they consider hard. I will note that if I give you something that's 3 stars out of 5, that's around the hardest problems that we'll ever put on an exam. I will note that no specific algorithm that I come up with here is going to be considered in scope. So you don't need to have these algorithms memorized. This is just purely for practice. All right. Everyone ready? All right. So let's start off with one that we've kind of looked at a bit before. You're given a list of n integers. They're currently unsorted. I want you to determine if the list contains at least one pair of duplicate items. So the first list contains 2 10s, so you would return true. The second list contains no duplicates, so you'd return false. N log n runtime, that's a 1 star difficulty. If you can get it to n runtime, that is a 2 star difficulty. Let's take 3 minutes to solve this one. And just FYI, even if you can't solve 3 stars within this time, don't worry about it. I am giving you like a really short amount of time to solve these. You'll have way more time on an exam to solve these questions. Oh. We've done this one time. Yes. Yeah. We added this last time. All right. Let's bring everyone back together. Did anyone have an n log n solution? Anyone have an n log n solution? Yeah. Yeah. You use merge sort. That takes n log n time. And then you use the same dupe2 algorithm that we came up with in the first asymptotics analysis lecture. You just compare adjacent items to see if any of them are the same. Anyone come up with the O of n solution? All right. Let's have an. I think you're new, right? Yeah. Yeah.
I was thinking like we create a new set and then add all n elements to that set with the set size is less than the size.
Yep. Create a set, add all the items one at a time into the set. If you get all the items in and there's n total items, then you have no unique items. Did anyone come up with any other solutions? Yeah.
We can create an array filled with -1, and we can have the index for each of those items, change it from -1 to 1, but then check if it's already 1. And if it's already 1, then you return.
Ooh, that's an interesting one. You create an array of like size large enough that it contains every single possible value. Yeah, that's effectively the same thing as an array index hash table. Yeah, similar things. Good point. Yeah.
We just do export it and then do the duplicate again.
Huh?
We just export it and then do the duplicate.
Yeah, you could also radix sort it. Our integers bounded by that. I will point out though that if you have more than 2 billion elements, uh, then we kind of assume we're in a universe where integers don't have an arbitrary maximum limit, in which case you do end up getting W, where W is like the number of digits in a number. As it turns out, the minimum number that W ends up being is log n, uh, because you just need at least log n digits to store n unique values. But yeah, at least for this problem, I would count like radix sort and then use dupe as a valid O of n answer. Yeah. All right. Another question. Here's actually a question that was on an exam, a 61B final exam from summer 24. So you're given a graph where the edges are values between 0 and 1, not inclusive. You have a start vertex and you have an end vertex. And I want you to find the path whose edges multiply to the largest possible value. So in this graph here, the maximum possible value you can get is this 0.6 times 0.7 times 0.8, which is 0.336. That's the largest possible value you can attain in the below graph. This is a 3-star difficulty question because it was on a final exam. Let's take another few minutes to solve this problem. Pass this. I just wanted to yeah. All right, let's bring everyone back. What do people think? Does anyone have a solution to this? Yeah. You take the log of everything and then use Dijkstra's. That is very close to the right answer. Unfortunately, this doesn't quite work because if you take the log of a number less than 1, you end up getting a bunch of negative numbers. Yeah. Also, we're trying to multiply to the largest value. If you run Dijkstra's, you'll get the smallest value. Yeah. Anyone have any other solutions? Yeah.
Send me to a like right first search and get every single possible like start to impact and then just choose the maximum time.
Look through every single possible path, choose the best one. That is a valid solution. It is going to be very slow. Yeah, I should have mentioned this is supposed to be polynomial time. Yeah. Take the maximum each possible step. That doesn't work necessarily, unfortunately. Different graphs are going to have different results depending on that. Yeah.
Like all values of null if you start out things like positive, like like switch the signs of everything.
Switch the signs of everything, then use Dijkstra. Dijkstra doesn't work on negative numbers. Sorry. Yep. Huh? Take the reciprocal and run Dijkstra's. That doesn't work. I don't have a counterexample for you right now because it is tricky, but it doesn't quite work because the sum of the reciprocals isn't necessarily going to be the same ordering as getting the product of a bunch of things. Yeah.
One minus the edge path or the edge weight, and then find the shortest path with Dijkstra's then you can.
One minus the edge weight. Unfortunately, that also doesn't work because the product is going to yield a different value as the sum of one minus edge weights. I think 4, 5, 6, 7, 8. Yeah, as an example, if you just did it on this graph, then you'd actually get a 0.4, 0.8 path here because this adds to 0.8, whereas this path adds to 0.9. Yeah.
You put a version of extras where instead of you're looking for the smallest path, you could just initialize all of the, and like normally in extras you initialize the lengths as like infinity,
Mhm.
you would just initialize them all as 0 and the starting one is 1. And then instead of like adding, you could just multiply the paths and then you're basically just looking doing the same thing, but instead of each time that you're looking at the adjacent edge paths, you don't take the smallest one, you take the maximum.
Yeah, that sounds like the solution that was intended on this exam. Yeah, solution one was effectively you run Dijkstra's, but you multiply instead of adding edge weights. You use a max heap instead of a min heap, and you start at 1 instead of infinity. This works because the product of weights always decreases, because we said that all the edges are between 0 and 1. Now, the 4-star difficulty solution, which you came really close to, is effectively doing the log. The only thing is you need to take the negative of the log, because that way you get to positive numbers. There it is. So if you minimize the sum of negative this logs, that's the same as maximizing the sum of log x plus log y plus log z, which is the same as maximizing log xyz, which is the same as maximizing xyz. So if you run Dijkstra's on the new graph, you should get the correct path. Now I'm going to make one minor modification. And just this minor modification is going to make this problem way, way harder. Instead of multiplying, I'm going to ask you to find the path that adds to the largest value without visiting any node more than once. Uh, this is hard enough. I'm only going to give you a minute or so to solve. So go ahead and feel free to discuss for a bit.
I wonder if we can do the log of the reciprocals, the max. The log. Say that's negative log. Yeah. Oh, okay. Yeah, there you go. Good point. Yeah, order of operations. Okay, because that's what I was. Yeah. Negative log. Yeah, sure is. Nice to be fair. I wasn't actually paying attention to your solution. I just solved it a bit different than like that person that was.
All right. Let's bring everyone back. Did anyone come up to any solution? Yes? All the reciprocals, then do the minimum spanning tree? Not really. The minimum spanning tree doesn't necessarily yield you a fast path from any 2 points. It's definitely not going to yield you the fastest path for every single possible pair. And the mid-spanning tree is going to be unique for every single graph. Yeah. So not quite. Any other solutions? Yeah, this one's a bit tricky. I actually do think I messed up a bit here because this graph is kind of hiding the difficulty. Yeah, there's currently no known solution in polynomial time. In fact, this is one of the Millennium problems, which if you manage to solve, you win $1 million because it is one of the seven problems that in 2000 was considered the most important problems to solve. Currently, only one of those seven have been solved. And the guy who solved that one declined the prize of $1 million for it.
That's the level of neurodivergence you need to solve things.
Yeah,
The other thing is, what's fun about this is like even a modestly sized graph, like a few hundred vertices, you can't do it. Even like 50 vertices, you can't find the longest path if it's dense.
yeah,
Just can't.
yeah. Although generally speaking, you can get
close.
approximations
Get
that are within
approximations,
2%.
yeah.
Yeah. Just looking at it as a human, you get close enough.
Yeah.
Now, I want to ask a question. Why is it that this earns you $1 million? I'm going to actually have you show why this gives you $1 million. The reason why is because this Hamilton path problem is a much more common problem that exists. And it's a problem of given a graph, determining if there's a path that goes through all the vertices exactly once. So this problem that we gave you, I'm going to call this problem X. I'm going to ask you to show that if you had a solution to this problem, the problem where you have a graph, edge weights are between 0 and 1, and you knew and you could find the largest path, can you use that to solve the Hamilton path problem? So if you have an efficient solution to this, show that you can solve Hamilton path efficiently. Let's take 2 minutes on this. All right, let's bring everyone back. Did anyone have a solution to this? Uh, yeah. Yes, it does make sense that this should be possible. Do you have an actual solution? Is there a way to do this? Okay. Yeah.
Or we can take the Hamilton path and then like divide it in such a way that all the values are between 0 and 1. And then if we run solution X through that, since it going through everything guarantees the maximum value, we can check if solution X has touched every vertex. If it has, then the Hamilton would also touch it, or there exists a solution. If not, then there doesn't exist a way to go through all of them.
So you take the graph, you divide all the weights by a certain amount so that they're all between 0 and 1. And then you run solution X. If that returns, let's say 5, what do you say?
Then you check, then you add up all the values of the weights. And if that adds up to 5, then you know it's gone through all of them. If it's less, then you know it hasn't.
Well, I think that's if you assume that the nodes have weights, not the edges. Because you might not be taking every single edge. Yeah.
So if you add up all the edge weights and you can keep that like edge weight total in mind, and then you use the maximum path. If that if this path goes to all, if there's a path that goes to all vertices, then the maximum path would be equal to the sum of the edges, of the total edges.
Yeah. Keep in mind that you're not necessarily going through all the edges, right? You might be missing some edges because you only want to go through every single node. Yeah. Yeah, this one's kind of tricky. Did you come up with?
Not really. I had a rough idea maybe, but go ahead.
Yeah, this one's actually a bit tricky. Yeah.
Pairs.
You just go by contradiction. Say if you have missing a vertex, and that means you put it at a longer path that would be longer than the maximum spanning tree.
Well, it's not a maximum standing tree, but you do have kind of an idea. Yeah, if you take a graph, here's kind of like my solution.
I'll tell you what I had in mind, but I think it's wrong.
Sure.
Which is
For context, this is the first time Josh has seen this slide.
yeah, and I'm also extremely sleep deprived. So my guess is I was thinking you consider every pair of vertices and all the edges are weight 1, and then you just see does there exist a path of length b minus 1.
You're
And
close.
but there's like one little extra step, which is you need to make sure that that end goes back to the start because it's
Hamilton path.
oh, Hamilton path. Oh, okay, so yeah. Anyway, that's my best guess, something like that. But tell me what the real answer.
All right, you're close. The solution
I didn't know why I needed non-integers. I didn't know why I needed not one.
The solution that I did was just you create a graph, just the same topology, but you set the edge rate 0.5.
Okay.
All right, so all the edges are 0.5. And then you create 2 dummy vertices. You create a vertex start that's connected to everything with edge weight 0.1. You create another one at the bottom with edge weight 0.1 as well. That's connected to everything. And you determine if there is a path from S to T that takes distance 0.2 plus 0.5 v minus 1.
Yours, I think mine works just slower than
yeah,
yours.
The way
you have to do every pair of vertices.
Yeah. So in effect, if we were able to run problem X on every pair of vertices, then if any of them has a 0.5 times v minus 1, then we've solved it. We found a path that takes v minus 1 edges. And if none of those pairs work, then we can't solve it at all.
So you save the factor of b squared.
Yeah.
Fine. Good job.
If we have a starting node and an ending node, then that saves the factor of b squared. We can do this in a single step.
It's like percolation.
Yeah. Yeah, this one's a bit tricky. I might. Yeah, this might be 4 stars. Anyway.
That's 3.
Okay. Anyway, I don't have time for this last question, so I'll just show it as you leave. There are solutions after this, but here's just the last question. If you have a line of W plates, you're given n pairs of numbers A and B. And what you do is that for each of these pairs of numbers, you place one bean on each plate from plate A to B. And I want you to give me solutions to these 3 problems. First off, can you determine the total number of beans in O of NW time? Can you find the total number of beans in O of N time? That'll give you a harder 3-star problem. The next question is if you can find the number of plates with an odd number of beans in N log N time. All right, I'll leave this up as you leave. Feel free to talk with me if you want to discuss the solutions. Otherwise, the solutions will be available on the next slide. Cool.
It leads into the bonus lectures better than the just in time. Like this is prep for reduction. The last week is T and P, world, all that. Okay, so this is like this time was like sort of I replayed. Oh, I made up. Some of these are inspired by some of these are
I got the first question for God. X. I didn't really get that.
yeah.
Probably.
Yeah, so it isn't that that's not what I'm saying. Like the maximum.
Maximum time. Yeah. It's like that. Oh, yeah, that's true. I was because I know Professor Huxer is yeah 70, but I can't think I'm 55
As of now, they're not.
I see. Are you doing anything?
I'm teaching 6
Oh, I'm really so. Wait, is it the session C? I didn't know that.
Oh, we only have one session for 6 years.
Set up your goal.
Oh, you so they actually had us in the solve that. Then that's nice. And the way you do that is you take that. You just create a possible graph. All that is going to have like yeah, that way you don't have to the length of the path. Yeah, all Linux commands. Now we put this look over. See if any of that. That's not quite. I could me identify then traverse inside, and then you'll compare.
It's a good feedback, like position. And you know that idea of surveying or like when like the shows because for the longest time
Because this is I mean, it is.
okay. This is spinning.
Yeah, but it's spinning. No. That's why you can what's the Java would be do you have a I mean, it is, but then it's It's very like saying almost like not all in. Check out you're saying like you're saying, oh yeah.
All this does something that causes C and miss.
I think that's maybe the same Jackson. Most Professor Hugs
No, maybe
most Professor Hugs.
It was. It does. It just runs in V squared attacks in V squared.
Oh,
So it's still positive.
so we'll see in summer then.
You'll learn you just can't have it. Because I probably
together. So it's just a little bit. So what we did is added this and added so much fun. And then we add the custom command.
If there's anything that like
and it's not multi-excising. Have you heard about that? Multiple excising. Yeah, it's
the first problem. Because we probably create
like you know how like a dwarf would get like a bigger spawn
and add for each of the pairs to flip, you add say in like one in 2 through 5 releases, which will be advertised constant time. Then it'll take enough computer time.
yes, the O of NW solution is you just you create a list of plates.
Yeah.
Right. For 2-5, you just rate them from 2 to 5 and play the on.
Okay, yes.
And so on.
Okay, perfect. And for the constant time, like O of N time, I was wondering if you could go through each of the pairs, take a differences between B and A, add one to it, and just sum the entire one. Okay.
You just take because each sequence tells you exactly how many pieces it's added. You don't matter. It doesn't matter.
Exactly. So why is it restart difficult?
it's running up like an old ass.
Okay. All right.
The fun one is determine how many pieces an odd number.
Yeah, I wasn't able to think of that.
That one's tricky. So it's a cool question.
That's true, but everyone just goes on.
It's solvable, right?
Yes, I have a solution on the next page.
Okay, got it.
Just like you allocated. I'm not giving you two unsolvable.
It's model like the price for like so Google pays like 20 cents per hour. Let's say it's cheaper. Like what is the next like something like that? Like that's true. That's true. But
It depends. One right. I would count it as
Oh, so like minimum amount of coding, but
it depends. Sometimes we also give you like just the
yeah. That already exists.
I don't know how it will be.
There's something else I just want to see. They should add some act. I said this, but always open on my fifth one. Yeah, like I have 5 different. So if I'm on the first one page, here and it's open state. It won't open here, it'll actually open automatically.
oh yeah.
They have all my instance auto open where there's
Let's see. Blue dungeon brick, honey block.
Oh yeah. The popularity of signal skyrocketed.
And then I was trying to
For what? It's just no, they use
like,
signal like this.
oh, I think that's like that.
Yeah, instead of using Pentagon security.
Like when I see the wall.
Yeah, or
Yeah.
No,
That's what like the special. You could see who it was. I just did like I googled
Yeah. Have a good one. See you around, folks.
Yes, Dan.
See you around.
Oh yeah. Still.
Somebody gets delicious. What's up?
Oh no.
Oh, you can press it on the direction.
But it's actually pretty hard. But I only made it as
Oh, nice.
and yeah.
Showcase.
And then
What's nightmare mode?
oh,
Strobing effect?
it's literally like, so when I was making it, like there's a, oh, now you can't activate it because you get all the cards. I never figured out how to change that. But like during the development of this, I realized that like if you cause standard show more than once, they'll like flicker, right?
Oh
So
no,
I
you
realized,
made that a
so I
feature?
just like intentionally made that. For example, made it flicker, which is, so it's basically the exact same code as the other one, but
Yeah, I've done that myself.
yeah.
The first game I made, I wanted to like make moving enemies, which were just circles. The way that I did it was I would draw a blue circle. And then the next frame, what I would do is I'd erase the blue circle.